Our first topic for this class is the current mirror. So, talk about why current mirrors are important. The first thing that we're going to address is why the resistor biasing schemes that we developed last quarter don't really work well for sensitive electronics. Okay. So let's look at a BJT resistive biasing scheme and just kind of a simplified version of it, where we have a voltage divider circuit that is effectively just biasing a BJT current source. And this current source here, let's call this Q1, might be being used to bias some other circuitry, which isn't particularly important. So I'm going to call this current IC1. This is IE1. This is IB1. And this is VBE. Okay. To make our life simple, we are going to assume that the base current is small. So if this guy is approximately 0, then our emitter current is approximately just IC1. And from this, our base emitter voltage, VBE1, is just VCC times R2 over R1 plus R2, and that will be equal to VT times the natural log of IC1 over IS1. Okay. So this equation gives us our DC operating point, right? We have our base emitter voltage and we have our collector current relationship all buried in here. So if we know one, we know the other. Okay. Well, this left-hand expression tells us that our DC operating point is extremely dependent on our supply voltage, right? So that if we have any variation in our supply voltage, then we have a variation in our DC operating point. So our voltage VBE1, which will in turn cause a variation in our collector current IC1. Over on the right-hand side here, we have two quantities, VT and IS1, that are very temperature dependent, right? So that if the operating point temperature of our device changes, VBE changes and IC changes in turn, right? Technically speaking, the resistors R1 and R2 will also experience temperature variations, but they will experience them in the same way. So it's really not going to mess with this guy too much. So this resistor biasing scheme is very temperature dependent and very power supply stability dependent. So let's look at a MOSFET, see if that fixes anything. Short answer is it absolutely doesn't. So for a MOSFET transistor, resistive biasing scheme, where we've got some resistor R1 and some resistor R2. Call this current ID1, since this is transistor M1. Let's call this voltage VGS1. Well, if our device is operating in the saturation region, then that means that the quantity ID1 is equal to 1/2 mu n C ox W over L, excuse me, times VGS minus VTH quantity squared, where I can express VGS using my resistor divider network, which establishes it. So we'll have UN Cox W over L VDD times R2 over R1 plus R2 minus VTH quantity squared. So the quantity VGS then obviously depends on a stable value for our supply voltage VDD. And if our supply voltage changes, then our drain current changes. The carrier mobility mu and the threshold voltage VTH are highly temperature dependent. So in this configuration, even with MOSFETs, we still see a high dependence on both temperature and power supply voltage. Okay. So you may be asking yourself, well, why does this matter? How many of you have a cell phone? Yeah, all of you should be raising your hands, obviously. Some of you are playing on them right? Your cell phone has several transistor-based circuits inside of it. What? Several, like millions. Yeah, quite possibly billions, okay? What if all of those circuits suffered from temperature and power supply dependencies, okay? The temperature dependency, I guess you could arguably get away with if you kind of stayed in one spot, you know, and in one room, the temperature is going to be relatively constant, but your power supply value isn't, right? Because your cell phone is powered by a battery whose voltage depends on its state of charge. So the more you use it, the more the state of charge changes and the more the voltage that's being supplied changes, right? So for a sensitive electronic device, obviously it has to be designed to operate over a range of voltages and a range of temperatures. And to facilitate that, we have to use devices that provide stability, okay? So I'm going to draw a circuit here. We are not going to analyze it. It is beyond the scope of this class, but this is the circuit that's used most often to provide these things, okay? So this is what's called a band gap reference circuit. This is something that we look at in 438. So for our band gap reference circuit, it's going to look something like this. Actually, sorry, I drew that transistor as an NMOS and it should be a PMOS. My apologies. So arguably things are already looking kind of terrible. We've got 4 transistors, and then we have these wackadoo feedback loops. And then just to really make things awful, they also contain BJTs. Oh, it's actually. Here's our ground. Here's a resistor R. So this is the thing that establishes the current. And then over here on the far right-hand side, we have this guy right here. Like so. And this establishes a reference current that can be used by other devices. We're literally not going to analyze this at all in this class. This is the simplified version of one of these guys. Yeah. We're going to talk about some of the parts of this in this class next, but effectively, what this circuit utilizes by using NMOS transistors and PMOS transistors is anything that has a positive temperature coefficient. So if it increases when temperature increases, has a counteracting device that has a negative temperature coefficient. So that effectively everything cancels each other out and it's extraordinarily temperature stable. It literally winds up referencing the band gap, the electrical band gap of a silicon crystal, which is constant 1.12 electron volts, regardless of what the temperature is, which is why it's called a band gap reference circuit. Everything works out to cancel out, and the output current that's applied depends on the value of the band gap of the semiconductor that's used. Okay? So this circuit is capable of providing extraordinarily stable values of current to whatever it is connected to. There are a couple of limitations in as much as it has multiple stable states, so we actually have to include what's called a startup circuit to make sure that the state it's stabled in isn't everything is off, which is a possibility, but that's a topic for 438 if you choose to suffer through that with me next one. All right, so the biggest limitation of this band gap reference circuit, which provides stable biasing currents for high performance microelectronic devices, is that it is physically large, which means if we needed one of these for every time we needed a stable current, our microelectronic devices wouldn't be microelectronic devices. They'd be much, much larger. So what we're going to talk about today is current mirroring, which is a circuit scheme that takes this reference current and makes copies of it. And since this is a stable current, all of the copies are inherently stable as well, to some extent. Okay. So current mirroring can be summarized with a very simple pictorial diagram. All right. So this is what our current mirroring scheme is going to look like. We have a reference current, IREF, that's being supplied by some stable current source like our band gap reference circuit. This current gets fed into what's called a current mirror circuit. And that current mirror circuit then generates a current, which we're going to call I copy. Okay. So we have a sense mechanism that measures what I reference is, and then a copy or generation mechanism that generates a copy of that current. Okay. So our first current mirror that we're going to talk about is the NPN BJT current mirror. So in an NPN BJT current mirror should be fairly obvious, but the copy current is going to be generated by a BJT current source. Seems kind of obvious, right? So we're going to have something that looks like this. Here's our reference current IREF. And then for now, we're going to call this bit here a black box. And this is our sense mechanism. A big question mark on it. Then here on the right-hand side, here's I copy. And this green box effectively represents the current mirror system or circuit as a whole. And I'm going to call this transistor, for the sake of argument, Q1. So let's talk about what Q1 is doing, okay? Creating this copy current. Well, how does it do that? Well, as we know by this point, or at least I hope we know by this point, a BJT can be utilized as a voltage controlled current source, right? So we have some voltage here, VBE1, which tells us exactly how much current I copy is. Okay. So we could say that I copy is simply IS1, where IS1 is the saturation current of transistor Q1, multiplied by EXP, the exponential of Vx over Vt. We know that for sure. Now what we want is for I copy to be equal to I ref. We literally want to make a copy of that stable reference current. So what this means is that if Q1 is functioning as a voltage-controlled voltage source, voltage-controlled current source, then whatever this black box is has to be operating as a current-controlled voltage source, because the output of this black box is supplying the base emitter voltage for Q1. Does that make sense? Okay. So we want Vx, the output voltage of our black box, to be given by Vt times the natural log of I ref over IS1. What circuit or circuit elements or whatever gives us this relationship? Another BJT. But specifically, a BJT that is diode connected. Okay. So if I replace my black box with this guy, let's call this Qref, I have satisfied my constraints under a very specific condition, and that is IS ref must be identical to IS1. Meaning that transistor Qref and transistor Q1 need to be perfectly matched, right? In that case, what's happening here is that our reference current is effectively forcing a current of IREF to flow through transistor QREF, which in turn, through this feedback loop, forces a voltage of Vx to occur between the base and emitter terminals of QREF, because that much voltage, that base emitter voltage drop has to be there in order for QREF to be carrying IREF. And then transistor Q1 has the exact same base emitter voltage, which means it must be carrying IREF as well. Does that make sense? Okay. So, one quick note here before we come up with better uses of this thing. That voltage, that base emitter voltage Vx, is temperature dependent, right? Because it depends on IS, which is inherently temperature dependent. But the quantity IREF and therefore I copy are not temperature dependent, okay? So effectively, any temperature change in this portion of the circuit doesn't get carried out to this guy, which in turn doesn't get carried out to this guy here. Because as the temperature goes up, IS is going to go up, Vx is going to go down, and is going to compensate for each other to provide that stable copy elsewhere. Okay. So this in and of itself is pretty useful. It's even more useful if we realize that we can make multiple copies, right? So I'm gonna, actually I'm not, I was gonna literally make a digital copy and then start drawing on that, but I know you guys hate that because you can't do it. So, yes.
When you mentioned the temperature dependence of these circuits, how much of that comes from heat generated by the circuit itself, like the circuit component itself?
So that's not really what we're considering. And so what I mean by that is the circuit is going to, if the circuit is at a steady state condition, then the temperature at which the circuit operates will be at a steady state condition as well due to ohmic losses and all that kind of stuff. So it's really temperature changes due to environmental changes that we're talking about. But you are absolutely right that there is going to be some inherent temperature instability while the device comes up to its thermal equilibrium. That's not really what we're concerned about here. So we're not worried about startup and turning off. We're worried about, okay, so the device is operating here in, I don't know, this room, which seems like it's 95 degrees, or outside where it's 40 degrees. It needs to be doing effectively the exact same thing. That's the kind of temperature stability that we're looking at. Does that make sense? Okay. All right, so let's redraw this guy real quick. Sorry, these should be C's. Here's QREF. Here's Q1. Let's call this I copy 1, and it's connected to some external circuitry. Okay. Now, what if I had another transistor? And I connected the base of this transistor, let's call it Q2, to the base of QREF and Q1. kind of current should it be carrying? Also, yeah, so sorry, I should have labeled this guy here. So we're going to call it I copy 2, but it's effectively I ref again. We can keep connecting multiple transistors as long as we connect their base node to the base of our current controlled voltage source Q ref, and we will effectively can make an infinite number of copies of our reference current. There is a caveat. That I'll introduce here, and then we'll talk about in detail shortly. So let's call this Q sub n, where this is I copy n. So the problem that we will see if we are making multiple copies of our reference current is that our current source here, IREF, has to supply the base currents of all of these BJTs too, right? So what I mean by that is most of IREF winds up flowing through the collector of QREF. And then a small portion of it obviously branches off to feed the base of QREF and the base of Q1. But as we add more and more copy transistors, more and more of this reference current gets used, providing the base currents to all of these guys, which in turn makes all of these copies a little bit less than IREF. And the more copies we make, the more error we introduce. Okay. We'll address that momentarily. So our current mirrors to this point are capable of providing, let's call it an exact, in quotation marks, copy of our reference current, something pretty close to an exact copy of our reference current. But what if, let's say for the sake of argument, this is providing 10 microamps of current, or this is providing 10 microamps of current, but we want something to be biased by 30 microamps of current. How do we do that? Well, we can get scaled versions of our reference current by connecting transistors in parallel. So let's look at case number 1. Scaling what I'm going to call Q copy. All right. So we take our basic current mirror, like so. And we make multiple copy transistors. So let's call this Q1, Q2, and all the way out here, Q sub n. So all of our bases are tied together. All of our emitters are tied together. So what we're going to do now is just tie all of our collectors together too, so that we have a single current here, I copy, that is in some way, shape, or form related to iReference. So let's figure out what that relationship is. So before we get into the math here, I want to explain exactly what we are doing here, even though it doesn't necessarily look like it. If you recall from 335, the saturation current for a BJT is AE, which was the base emitter area. So the area of the base emitter junction multiplied by Q dN times Ni squared all over NB, the dopant concentration of the base, times WB, which is the physical width of the base. Well, when we put transistors in parallel, we're effectively just making AE larger because there are 3 base emitter junctions now. Everything else literally stays exactly the same. By connecting transistors in parallel, we make it look like a transistor that is n times as large as a single transistor. Okay. So for this first case, where IREF is equal to IS times EXP of Vx over Vt, or I should label Vx here just for argument's sake. We're going to have I copy is equal to N times IS EXP Vx over Vt, and therefore I copy is just N times IREF. So if we connect multiple copy resistors together in parallel, we can get integer multiples of our reference current, which is useful. Now let's talk about what happens if we scale our reference or sense transistor. I'm going to need to go to the next page. Write this. Case number 2. Scaling QREF. All right, so say that we have our reference current like so. Here's what we're going to call QREF1. And we're going to make a copy of that. And potentially further copies depending on the size that we want. Like so. So let's call this QREF2, QREF3. To connect all of these guys in parallel, we're going to have to tie their bases together. Like so. We have to tie their emitters together, like so. And then we also need that feedback from the collector to the base. And finally, on this side, we have our copy transistor Q1. And then here is our copy current. All right. So in this case, and sorry, instead of calling this 3, I'm going to call it QREF M. So we have IREF is equal to M times IS EXP Vx over Vt. This is our voltage Vx. I copy is IS times EXP of Vx over Vt, which comes out to be 1 over M times our reference current. So effectively what's happening here is our reference current effectively divides itself up equally between these 3 or however many M reference transistors. And since each of these individual transistors is only carrying a portion, Vx gets smaller. And so we get a scaled down version of our copy current, right? Yes.
Why do we have only for glass?
Technically, it'll be for all of them, but it doesn't particularly matter, right? So all the bases are tied together and all of the collectors are tied together because it's just one big node. So with our first case, we were able to get integer multiples of our reference current. With our second case, we can get, I guess, call it integer fractions of our reference current. I'm not really sure how to describe it. When we get fractional portions, we can do both at the same time. And what we'll find is that we get effectively just N over M times our reference current, right? So case number 3, scaling Q copy and QREF. This would look like VCC IREF goes here. Here's Q ref 1. Here's Q ref M. Then over on this side, here's Q1, here's QN. And let's see, here is our copy current, which will be approximately N over M times IREF. We can really scale our reference current to any value that we want. It just depends on how much real estate we're willing to expend to do it, since it requires us to put several transistors in parallel. Okay. All right, so as I mentioned previously, whenever we have too many transistors connected to this reference current, we start to see that our copy current has some error associated with it because this reference current has to supply the base current to all of these guys as well. Okay. So we're going to work an example that illustrates what that error is. And it might be the last thing we do today. So our goal here is to determine the percent error in the mirror currents if beta is equal to 100 for all of our BJTs in this circuit. Okay. And our circuit of interest is this guy here. Where here we have IREF. And then our sense transistor is going to have effectively a total area of twice AE. So this is a shorthand for saying there are two reference transistors in parallel. And that is going to be supplying current to this first transistor, which has an area of 3 AE. So this is the one we're going to call Q1. This is Qref. This is our current I1. And then we're also going to have a second set of copy transistors having an area of 5 AE. We'll call this guy Q2, and this guy carries a current of I2. And here is our connection. So this is our circuit that we're looking at. All right. So without including any error, what should the relationship between I1 and IREF? How many IREFs is I1? N is 3, M is 2, so it's 3 halves IREF. What should I2 be? 5 halves IREF. Right? Okay. So let's call this node X. And I'm going to illustrate, we're going to apply KCL at node X, so I need to pay attention to the currents that are leaving node X, okay? So let's do those in red. So we're going to have this current right here, which I'm going to call IC ref, because it's the collector current for our reference combination of transistors. We all okay with that? We're going to have this current which is IB ref, because it's the base current for our reference, right? It's also leaving node X. Are we okay with that? We're going to have this current. I'm going to call IB1, the base current for our combination of transistors making up Q1. And then we're going to have this guy down here, which I'm going to call IB2. So this is the base current for the combination of transistors that's forming Q2. Those are all the currents that are leaving node X. Yay or nay? Yeah. All right, so if we apply KCL at node X, what we find is that IREF is equal to ICREF plus IBREF plus IB1 plus IB2. Are we okay with that? All right. Well, obviously, IBREF is just ICREF over beta. Right? So we're going to have ICREF plus an ICREF over beta. Well, if I1, which is the collector current for transistor Q1, is 3/2 IREF, then IB1 should be 3/2 ICREF over beta. And similarly, IB2 should be 5 ICREF over twice beta. So we can factor out ICREF and we're going to call that 1 ICREF twice beta over twice beta. We're going to call that 1 over beta times ICREF 2 over twice beta. And then we're going to have 3 over twice beta and 5 over twice beta, which gives us ICREF is equal to, excuse me, ICREF multiplied by, my apologies there, twice beta plus 10 over twice beta. So this term right here represents in some shape or form the error between IREF and ICREF caused by all of those transistors being connected. Not done, I just wanted to point something out there, okay? Since ICREF is 2/3 I1, twice beta plus 10 over twice beta And I got that from this relationship right here, where we're saying that effectively IREF and ICREF are supposed to be effectively the same thing. I can rearrange and find that I1 is 3/2 IREF times twice beta over twice beta plus 10. And it shouldn't be hard to see that I2 would be 5/2 IREF times that same factor of twice beta over twice beta plus 10. So what this is telling us is that obviously twice beta is smaller than twice beta plus 10. So our copy current I1 and our copy current I2 are slightly smaller than their expected values of 3/2 IREF and 5/2 IREF, right? So this bit right here represents the error. From this, our error E for our copy currents is just 1 minus twice beta over twice beta plus 10, which comes out to be 4.762. So our currents are 4.762% smaller than we would expect because of the number of transistors that we have connected. Everybody okay with this example? All right, so this is the last thing that we're going to cover today. When we get back on Friday, what we're going to do is talk about a scheme that we can employ to minimize this error, okay? Then we're going to talk about PNP current mirrors, which will be pretty brief, and then get into MOSFET current mirrors, and then that'll be Friday, and then finally on Monday, we'll wrap up current mirrors by introducing Cascode, Wilson, and Widlar current mirrors. So topologies that are used to effectively make current mirrors have a much larger output resistance so that they look closer to an ideal current source to whatever they're connected to. All right, that's enough out of me.